And a quadratic function, y equals x squared, would look something like this. And a square root function, y equals x to the half, looks like that. So it looks like a quadratic function on its side. Because if y is equal to x squared, or if y is equal to x, then x is equal to y squared. So this function is just the same as this function when rotated by 90 degrees. So it looks like that. So I start out, and I plot this function, y equals x times a half, and I have the 45-degree line in there. This is y equals x. And so this is the low order one, and this is the high order one. So which one should I use? So if I get sleepy up here, just use the high order one. Okay, so I start out with a particular value, and I'll call this x times 0. And now I want to look at what the corresponding y is. So I go to the line, and then I get the corresponding y. But I'm calling the y x at time 1, because this is x0 gives me x1. So y equals f of x, or x at t plus 1 equals f of x of t. So if I've got x0, I'm looking up x1. If I've got x1, I'm looking up x2. So I start at x0, and I look up x1. Now, how do I plot x1 back onto this axis? How do I do that? I go to the 45-degree line, because that's where y equals x. So if I go to the 45-degree line and I go down here, then that will be the value x1. Everybody follow that? Okay, now if I start with x1 and I look it up, and I go across, I'll call that x2. x1 maps to x2. x0 maps to x1. Now I go to the 45-degree line, and I go down again, and I go to x2. So there's actually a shortcut, and the shortcut is I go to the line, I go to the 45-degree line, I go to the line, I go to the 45-degree line, I go to the line. And I can work, and I can pick up the sequence of values, x1, x2, x3. So that's exactly what we see in this picture. So the solution approaches this point. Now this point is where I've got two lines, y equals f of x, and I've got y equals x. This is the line y equals x, and then that's the line y equals f of x. And where they intersect, that's where f of x is equal to x. Now if f of x equals x, it means that if I start at this point, and I'll call this point x star, then I come across and I get exactly the same value, x star, because that's the 45-degree line. So if I start at that point, I'll always stay at that point. So it's called the equilibrium point. So x star is the equilibrium point. Equilibrium meaning unchanging. So wherever f of x equals x, that's how I find the equilibrium point. Okay? And so you can see here that when I start up at the top, I move into this equilibrium point, and if I start below, I will also move up to this equilibrium point. So now we come to this Beaverton and Holt, this generalized one, where r is equal to 3, and g is equal to 6, and k is equal to 100. This is what the curve will look like. This is the equilibrium point. If I started at some value here, I go to the line, then I go to the 45-degree line. Then at the 45-degree line, I go down to the line again, and then I go to the 45-degree line. And you'll see that as I continue, then I go up to the line, to the 45-degree line, down to the line. So depending on the shape of this curve, you'll see that this starts to go around, but it doesn't have any regular behavior. It's not like in the previous example, which was the square root, where all points eventually go up, or all points eventually come down. And they're going towards this equilibrium. Here, there is an equilibrium, and the equilibrium is this point, but I'm sort of doing all sorts of things. I'm going around it in many ways. I go there. So you can see that when the shape of this has a hump in it, that the solutions can go round and round, and they don't necessarily go round in a regular way, depending on the shape of this curve. Yeah, I had a question over there. Yeah, so this is, we've got this as a dotted line, but this is y equals x, this is y equals f of x. And in particular, we're just looking at y equals f of x, but in our model, we think of x as x at time t, and y as x at time t plus 1, then we're generating a sequence of points. So there are two curves. The one is this curve that describes the right-hand side of the equation, and then as I go around this and I calculate the next values, you'll see these values go up and down, and so that basically, over time, what happens is the solution basically looks like, it looks like this. So over time, I get a sequence of values. Here, the sequence is chaotic. Here, it's regular. And when I run the model, you saw that I get these different outcomes. So you have two ways of understanding this. One is to make a numerical model, and the other is to make a graphical model, or to draw the equation, graphically to draw the equations, and to use this cobwebbing technique. Now in the book you'll find other examples where we use the cobwebbing technique. The cobwebbing technique is obviously obsolete in the sense that you don't need it if you've got a computer, and you've got Nova to calculate the answers for you. But over here you see exactly why you can get chaotic behavior coming in. Okay, so that's pretty much for what I wanted to cover today. Let's see if is there anything else. So in a future lecture, we're going to talk about the logistic equation, and we're going to talk about some more ideas about how to discuss the stability of the equations. In the case where the answer asymptotically approaches, the trajectory asymptotically approaches a point, as we saw, then we say that the equilibrium is stable. But where it oscillates, we say it's unstable. And so how do we understand that? And we're going to understand that in the context of studying what's called this logistic equation in more detail in the fourth lecture. Any questions? Okay, so I'll see you guys on Thursday, and I would suggest that you should download Nova now and try to start playing around with it. And then when you come on Monday to lab, if you're having problems, we can help you with the problems, but it doesn't make sense to start at the very beginning on Monday in the lab.